Hello everyone, welcome back. So, in the last class we looked at some explicit schemes to solve the convection diffusion, linear and nonlinear problems. So, what we saw what I mean by explicit is that when we had this schemes like something on the left hand side and let us say something on the right hand side, right. So, whatever the special derivative that we had, we calculated in terms of the given time step. So, let us say this is a n. So, you know the value at function u at n and you want to go to n plus 1, right. This is your time, and this is your space, right. So, you express this u from the value known value of u here, you also calculated du by dx at this time step, right. And then using these values we marched in time. So, what we did here is we wrote it like minus c, and let us say if you are using FTBS. So, this will be basically u I n minus u I minus 1 n by delta x, right. So, this is approximating this du by dx at time n, correct, and this was written as u I n plus 1 minus u I n by delta t. So, this was the FTBS, and we saw that this kind of schemes are stable for lambda less than 1, right. Similarly, for the diffusion problem, we saw that this kind of problems where you use this FTCS scheme for the diffusion problem are stable for lambda d less than 0.5. And then we ask the question, is there any way we can increase the stability limit? Yes, we can. So, let us see how we can do that. So, this is what we did. Let us start with the diffusion problem. Okay. This was the diffusion problem that we had earlier, right, and we discussed that nu cannot be negative, right. It represents a viscosity kind of thing here. So, this is the explicit scheme where everything here in terms of written is in terms of n. Okay. And now, we are writing this all thing in terms of n plus 1. So, what we are doing here is that for this double derivative that du by dx square, what we are doing is we are writing in terms of uh, next time step. So, this is your n and this is your n plus 1. Okay. So, this is again the same what we are doing. This is the Euler, is called the Euler scheme. Okay, u I n plus 1 minus u I n by delta t nu, but for this one I am writing as if I know the value of n plus 1 everywhere on the right hand side, right. So, if I knew the value of n plus 1, which we do not, then how would the this will look like? The same central differential scheme that we had used earlier. So, this is basically u I plus 1, instead of n I will write it as n plus 1, okay, minus 2 u I n plus 1 and plus u I minus 1 n plus 1 by delta x square, right. So, remember we do not know the value of n plus 1 yet, right. So, we know the value at only at n, right. So, we want to march to n plus 1 and while doing that we are writing this in this form. Okay, it will things will become clear, because what you can do, you can still separate the values at n plus 1 on left hand side, whatever you n plus 1 on the left hand side and whatever values on the basically on right hand side. Okay, something like this you can write, and then you can solve this so that you can calculate the value of u n plus 1, correct. So, that is why it is called implicit, because we do not know the value here, and that is why it forms a basically linear system of equations which needs to be solved simultaneously, right. So, now you take the n plus 1 on the left hand side, all the okay, there is one more term n here, okay, and then you have all this n plus 1. I will separate it later. So, now here what we are doing, we are doing all the n on the right hand side, all the n plus 1 in the left hand side, right. I am using this nu lambda d is equal to nu delta t by del x square, right. So, if you basically collect all the terms, so this is start with let us say u I minus 1, and so if you take this thing, so this is everything multiplied by lambda d. So, this is minus lambda d u I minus 1 n plus 1. I have taken this term, now you take this term. Okay. So, this is I n plus 1 is here also and here also. If it goes on the left hand side, it will become 1 plus 2 lambda d u I n plus 1, right. And similarly, you can take this u I plus 1 n plus 1, that will become minus lambda d u I plus 1 n plus 1, right, is equal to u I n, right. That is what is written here. So, now we have collected this n on one side, on right hand side, and n plus 1 on left hand side, and our goal is to basically calculate all these u I n plus 1 or u I minus 1 n plus 1, u I n plus n plus 1 simultaneously in terms of by using the value of all the u I n's. Okay. So, let us select a simple grid here, okay, only 4 points here, and out of these, this 1 and 4 are basically the boundary conditions. Basically, now they have only 2 points here, right. So, write this expression here. I am doing it to basically illustrate how this method works. Okay. So, now the first one is a boundary condition. So, this will not change, that is why it is called the boundary condition. Although there are some boundary conditions basically which are time dependent, I am not going to discuss there that here, but right now let us see that the boundary conditions 1 and 4 are fixed. So, let us say it is a string where the value 0, value of u is 0 at both the boundaries, correct. So, this is u 1 n plus 1 equal to 0 and u 4 n plus 1 equal to 0, basically the ends are fixed, correct. And now, if you take this expression for the internal points, so when you are writing about 2, the I equal to 2. So, I minus 1 is 1 and I plus 1 is 3. So, you put all these things here, this is 1, 2 and 3 and everything is written in n plus 1 and this is u 2 n. Similarly, you do for 3, okay. So, then this is u 3 n and there will be 2, 3 and 4, right. So, you can write this entire thing in the matrix form. So, basically what you need to do, you write all this is u 1 n plus 1, u 2 n plus 1, u 3 n plus 1, u 4 n plus 1 and some matrix multiplying with this is equal to right hand side is basically now it is 0, u 2 n, u 3 n and 0, right. And this is the matrix you can write in terms of minus lambda d 1 plus 2 lambda d minus lambda d and so on and so forth, right. So, of course, if we look at the first element, just this is 1 and all others are 0, right. This is only, this will multiply, this row will multiply to this and it will get this. Similarly, the last one, if you look at, all others are 0, only the this one is present, right. When I am using the Dirichlet boundary condition, of course, you can use some other boundary condition or you may have some other value like 1 here or some other thing, accordingly it will modify here, right. Now, if you look at the central one, right. So, minus lambda d multiplies to u 1 n plus 1. So, this will become minus lambda d. This one multiplies to u 2 n plus 1, this is 1 plus 2 lambda d and this is again minus lambda d and the fourth one is 0, nothing multiplies to u 4 n plus 1, right. If you go to the next one, this will become 0, the first one nothing multiplies to u 1 n plus 1 and then this will be minus lambda d 1 plus 2 lambda d and lambda d minus lambda d, right. Now, all these things you know, lambda d is something that you fix, right. Your either you fix or you calculate using nu delta t by del x square, right. By fixing your delta t and delta x, nu is given as a parameter, right. So, you can write this entire matrix, you know the value at n and this is now basically a u n plus 1 is equal to u n, correct. So, if you want to solve it, this there are several solvers, you have to invert this matrix, this is a inverse u n, right. So, the matrix inversion is involved, you cannot solve, I mean get it explicitly, only the first one is explicit because those are boundary condition, only the last one is explicit because of the boundary condition, all other interior points are basically implicit, right. So, in order to get all these things, you need to solve this entire system of equations, and if your equation the matrix becomes bigger and bigger, the inversion is computationally becomes computationally more and more expensive, right. So, that is the challenge with this kind of solvers, but what is the advantage we will see shortly. Okay. Yeah, so this is what I spoke, that you can write this in terms of this matrix, okay, and then you have these boundary interior points and this is the right hand side. You can also basically, I mean to make it more elegant, what you can do is that you can define an operator, right. So, now what does operator do? So, for example, you can say that you want to write this delta u by del x square. So, this operation, this double derivative is an operator. So, this is L which is working on u, okay, and gives you this. Okay, and then you can probably take this maybe delta x square, because you don't want to write it everything in term. You can write it here, but you can take this separate also, right. So, this entire thing is written like this, okay, where L is the operator working on u I n plus 1, okay, and gives you this, because ultimately you are going to get the derivative of. So, when you are writing it, your this entire thing is in for I, right. So, when you write del to u by del x square at I, then you get this, right. So, this is why this is u I, but the time is n plus 1, right. And how does this L operator looks like? So, the L operator, so if I write in the in form of the matrix that we discussed earlier. So, we will have this, all this I term will be on the center. So, this will be minus 2, minus 2, minus 2 everywhere, and then there will be off diagonal terms, okay, 1, 1, 1, 1. So, this is how it will become like this, and all these other terms will become 0, right. So, this is how it will look like. So, this is called a tri-diagonal matrix. You have a diagonal term, and then you have off diagonal terms, this and this, and so on and so forth, right. So, these are the tri-diagonal matrices, and there are a lot of solvers to solve this. I think I spoke about this earlier. Those are called the TDMA solver, or the, I mean, one such algorithm is called the Thomas algorithm, which can be employed to solve this more efficiently. I mean, for a, of course, very large matrices. So, this is a well developed area, okay, how to solve this TDMA solver. I think I talked in the context of compact schemes, right, where you also have this implicit nature, right. So, then if you have all those things, then what you can do, you can write this entire thing, this entire matrix in the form of this. So, I am collecting this u I n plus 1 everywhere, and this new delta t by del x square is lambda d. So, this is basically 1 minus lambda d L u n plus 1 is equal to u n, right. And so, this is, sorry, I minus, so I is the identity matrix, right. You all know about the identity matrix, and then I subtract this lambda d, and this is the L matrix, right. So, then it will become the, so these are the interior terms, of course, there will be two boundary terms, right. So, this is an compact way of expressing the same thing, and if you want to write a code, right. So, this is basically I minus lambda d L u 1 plus 1 written including the boundary terms, and this is the A matrix. So, you will initialize. So, you can write it all the I minus 1, okay, term is minus lambda d, all the I terms as 1 plus 2 lambda d, all the I plus 1 term as minus lambda d, right. And then you give this Dirichlet boundary conditions, this is 1 and 1, okay, on the top and the last element of the matrix, and then you have to use any linear algebra solver. I have used Python, but you can use MATLAB, and you can just do inverse A into uh, B, okay, or the right hand side that you have, which is RHS here. The RHS is nothing but all the values, okay. So, this is all the u values, and the boundary condition, which is 0 and 0, correct, and you can just march in time. So, there are many ways of solving this. You can do, I think, solve A comma RHS if you are using MATLAB, or you can just take the inversion of A and inverse of A and multiply with RHS, and so on and so forth, right, or you can use a TDMA solver, right. So, this was an explicit case when the lambda d was 0.501, this is what we saw in the last class, and nu equal to 0.1. Let us see what happens when you use the implicit with the same lambda d greater than 0.5, and we see that it is very, I mean, it gives you the correct solution, okay, even at the higher CFL number, right, greater than lambda d greater than 0.5, okay. Not only that, if you go to, let us say, high CFL number, even at lambda equal to 10, it is giving you the correct result. In fact, I tried with for this case very high diffusivity, I tried with 100, 500, even 1000, it was basically not blowing up. When I went to very high value, okay, I saw that it blew up and it does not give you the correct result. Okay. In fact, I mean, I did not see the solution of 0.2 and 0.4 are basically on top of one another. If you increase further, it will give you a very bad result. So, there is a limit from practical purpose, that how big you can go for lambda d, but theoretically, as we will see in the next few classes that for the implicit schemes it is always stable regardless of what lambda d you have, right. So, that is the advantage of lambda d. From the practical point of view, I mean you have certain domain, and if you use the lambda d which is very large, that means what you did is you use the delta t which is basically much bigger than delta x square, okay, delta x square by nu actually, right. So, it is basically let us say this is your domain and you gave some disturbance here and use the value which is basically going even out of this, right. So, those kind of course delta t are not allowed, but theoretically we will see that these kind of equations systems are basically stable for any delta t, right. So, this is the beauty of the implicit scheme, and if you use let us say less diffusivity or the less viscosity, right. So, it gives you correct result for lambda equal to 100, but then it basically start giving wrong result very early lambda equal to 200. So, it also depends on how much uh, diffusivity you have in your system. Okay. Now, let us go to another scheme, okay, which is called the Crank-Nicolson scheme. So, what we saw earlier was called the backward Euler. Okay. So, backward Euler is very popular when you are trying to solve basically any steady state problem. You start with a time marching technique, some delta t, but then you want to go to the final stage and you want to make big jumps, okay, big jumps of delta t, so that you can reach to the final stage faster, right. In those cases the backward Euler is useful because it allows you to take bigger delta t, reasonably big delta t in practical problems without basically blowing up. But the backward Eulers are basically the first order scheme, and in terms of time accuracy they only give the first order accuracy, like we have for the spatial accuracy the spatial order, similarly have the order in time also. So, then we have something called Crank-Nicolson scheme which gives you the second order of accuracy, and what we do here is that is the same problem that we have basically del u by del t equal to nu del t u by del x square. So, in the explicit Euler we had this, that this was represented in terms of n, okay. In the implicit we had this is n plus 1, this was explicit. So, you use the central differencing, but in terms of n, this was the implicit center, you the same the central differencing, but assume that you know the value at n plus 1, right. What Crank-Nicolson scheme says is that you can take an average of these two, right. So, you have a part which is coming due to the explicit, your part which is coming due to the implicit, okay, and take the half of that 1 by 2, and rest all things are same, okay. And so, you can use the same operator that we had defined earlier. So, collect all these n plus 1 terms here. So, all these n plus 1 term can go on the left, and there is also one n plus 1 term here. So, this will get added here, and this is basically lambda d by 2, right. So, you can write this I minus lambda d by 2 u n plus 1, right, and then the right hand side is basically this is I plus lambda d 2 into this is the L operator that you have, right. So, this is how it will look like, okay. So, earlier identity will be just 1 1 1 1, and then you have this minus lambda d by 2 L that you have to add in the off diagonal terms here, okay. And because this L value is 2 here, so this will become 1 plus lambda d, 1 plus lambda d, 1 plus lambda d, and so on and so forth. Remember the L matrix that we discussed earlier, right. This is the L matrix, right, actually, yeah. So, this is basically minus 2, 1, 1, and so on and so forth. So, now there is a negative sign, this becomes minus lambda d by 2, and this is becomes plus 2 lambda d by 2, right. So, this becomes plus lambda d. This is on the left hand side, and similarly you can write this thing in the right hand side also, because you know the L matrix, right. So, this is only the interior points. If you include let us say the boundary points also, so then you will have these extra points here which is coming to the boundary conditions, okay, here and here also, okay, and this could be the value is 0 and 0. So, that could be the boundary conditions, right. So, now if you solve it, so again the Crank-Nicolson, as I told you, it is an implicit scheme and it allows for a higher lambda d. So, you can see that even at lambda d equal to 10 it is working fine, Okay, and uh, when you go to high lambda d, let us say what we did for the backward Euler at 2000 and all, it basically it's you can see that the scheme does not give you the correct solution, it starts behaving like it is blowing up, right. So, the lesson is that you cannot use arbitrarily high value, but you can go to reasonably high value, like unlike an explicit scheme where you can use only up to 0.5. The implicit allows you to very high value, typically in we use like values like 5 or 10 kind of thing. Okay, and if you are basically not interested in what happens at the intermediate step, you can go to even higher values of lambda d, provided that it should basically not blow up like this, or it should not be very high. Okay. Now, so we have looked at some of these schemes. Okay, implicit, explicit, FTCS, FDBS, and we saw that some schemes are good for convection, some schemes are good for diffusion. So, now the natural question that comes to our mind is that what kind of conditions we should impose on a numerical scheme to obtain acceptable approximation to the problem. That means, of course, we have conditions like stability. Okay, that is one part. Then I keep on talking about numerical diffusion, right. I said that once you are solving this problem, if it should only diffuse like this, okay, if it is a linear convection, but then you get something like this, right. So, it gets slightly diffused even if there is no diffusion in the problem for the linear convection. So, there is something called numerical diffusion. So, which basically reduces the accuracy, right. So, stability is one part, then we have accuracy, which is another part. Okay. And then there are other things which we will see in the subsequent classes, for example, resolution, basically the wave number or the wave property, then we will have basically consistency, and these kind of things we will look at the next few classes, right. So, what kind of properties or what kind of property we should look for a numerical scheme, so that it gives you the acceptable solution to the problem. And why do various schemes? So, right now we have seen what is happening, we have not gone into why it is happening, right. So, why lambda greater than 1 does not work, right, or why the implicit schemes give you the infinite stability, well, basically stability very high delta t, right. And how do you predict this, right, and for a stable scheme, how do we, like, how much is the error? I mean, of course, we talked about the truncation error and all, but we have not looked at from a uh, PD point of view. For example, if you want to solve linear convection or diffusion, so it is not only the time derivative or the spatial derivative, but it is the combination of both, right. So, for those kind of things, how do we look at the accuracy of the scheme acting on that system, right, and basically what kind of, when you use a PD, when you approximate a PD with a certain scheme, let us say FTBS or FTCS, what is it actually we are solving? Or the other question I should rephrase is that when you say finite forward in time and backward in space, we are making approximation in both the time as well as space, because these are both coming from the Taylor series and we are leaving higher order terms, right. So, what are the impact of basically not including those higher order terms in our actual numerical scheme, right. So, we will look into all these systems, all these properties in the next classes. So, basically what we will start with is basically we will take a PDE and basically write in differential equation form, like we have been doing using either FTBS or FTCS for convection or for diffusion, and then we will analyze the terms which we are not including, especially the leading truncation terms, and then we will get the information about the stability as well as the information about the accuracy from this. I mean, we will have some indication from that. Of course, we can do it only for the linear systems in the beginning, and then we will have some comments about the nonlinear systems later. Okay, with that, I will stop here. Thank you very much.